You can see the agenda here, the timetable. We will start with an introduction delivered by Ana Lima, who's the project coordinator. Then we will talk about the recycling routes of wind turbine blade waste. The presentation will be done by Dionis and Maria from NTUA. We continue with valorization of wind turbine blade waste into reinforced polypropylene composites. Presentation made by Shashank from TUE. Another presentation from TUE will continue on cold bonded lightweight aggregates rich in wind turbine blade waste. We have to plan a coffee break for 10 minutes at least, so that we have a smooth process. Then we talk about circular innovation construction by a presentation made by Tung from Holcim. Another presentation on how we can use the blade waste as reinforcement for cementitious composite. A couple presentation by Tao and Cynthia from DDU and IBAC. And we finish with a presentation which will mainly focus on the industrial large-scale applications. Presentation which will be done by Tung from Holcim and David and Rose from RWTH Aachen. Then we close and wrap up. And in between the presentations, we have like a Q&A session, so you can ask anything regarding the topics we'll be presenting. And at the end of the presentation, we also have a QR code where you can scan. This is a survey, an internal survey, so you scan with your mobile at the end of each presentation, and then you will see some questions that are made by the consortium, and that would be very interesting and very important for us to share your feedback based on the questions that will appear. I think, Anna, we can start.
Thank you so much, Haris. First of all, thank you so much for taking the lead in organizing this event. Thank you to all partners for their hard work so far and for sharing their results today with us. It's been quite a nice path together that we have crossed through the last 3 years and a half, three and a half years, almost 4. I've been lucky enough to coordinate this consortium to its almost completion, and this webinar serves as a little bit of as a demonstration of it. So I'll just start with what BLADES2BUILD is, or proposed to be and has become. The consortium is between these 4 universities and several industries, as you can see here. If you can go to the next slide, you'll see the different institutions as we go through the day. But here is a picture of us, our latest joint event. It was in January 2026 when we actually opened the demonstration, or went to the opening of the demonstration plant in Tudela del Duero in Spain, at the PreZero installations, the new installations. So we are a few, as you can see here in the picture. Go to the next slide, please, Haris. So the ambition of the project was a threefold one, and I will start from the bottom up. So the project once and succeeded in having wind turbine blade waste being integrated into the construction sector and the construction industry. And we wanted to do this by threefold. The lowest hanging fruit, that we call it, was recycling the blade and glass fiber textile scraps from the wind blade manufacturing into cement clinker co-processing. This is the lowest R, as you can see here in the right-hand side, in the R framework, circularity framework. Then we propose to repurpose the individual material constituents of the blade into construction products like concrete, asphalt, and so on. So there's a less energy intensive process here in R7, and let's go to a repurpose than it was in R8 and R9, where we propose to recycle the fibers. And lastly, there's the goal to repair the wind blades themselves for the reuse of the blades as a blade itself. So a little bit out of the scope from the construction sector, but still a higher goal in terms of circularity. So if you're not familiar with the R framework, you can have it. You have it here. You go from refuse, rethink, reduce, the narrow scope, then to reuse, repair, refurbish, remanufacture, and repurpose, where we prolong the use of the products in the use phase, and recycle and recover, which closes the loop, meaning that the components of the different products can be used again, either in its own supply chain, a value chain, in a closed loop, or outside of their value chain in an open loop, which is the goal here today. If we go to the next slide, please. So just to give you an idea of what we are working with, please, Hadis, the next slide. We can see that in this slide from RWTH, they show the blades, and we can see that in the middle picture here, you can see the end of life wind turbine blade waste that has been crushed, and above it a little bit of a smaller size fraction of this waste. If we go to the next slide, the next one, please, Haris. We propose to characterize this wind turbine blade waste into different methods and recycle them through solvolysis and pyrolysis. We also aim to use, like we said, in R8, R9 in the framework. Then we have R7, develop circular building materials with the wind turbine blade waste with a repurposed route. And then to enable this, we aim to build a demonstration plant to recycle end-of-life wind turbine blade waste. That's a high TRL demonstration of this project, and then a spin-off out of this with a turbine blade waste that is out of this demonstration plant. We aim to have industrial scale demonstrations where this blade waste is used in the construction sector. So if we go to the next slide, we will have N2A talking about solvolysis and pyrolysis, the two recycling routes, that we have considered in the project. In the next slide, please, Haris. Next slide. Then we have the developed circular building materials with wind turbine blade waste. And, we have achieved quite a bit of replacement theories through the project. One is the reinforcement concept, where we replace the reinforcements in concrete with some of this blade waste. Other is the replacement concept, which is replacing the fine aggregates, the coarse aggregates, or the cement with this blade waste. And the hybrid, which is a bit of reinforcement and a bit of a replacement concept. So throughout the day, you'll see a few of these examples by our different partners. If you go to the next slide, please, Haris. one key aspect is the demonstration plant that that PreZero has established in Spain. So if we go to the next slide, we have it located here in Tudela del Duero and in Spain, and it's led by PreZero, and we will hopefully we'll hear a little bit more about it later today. Next slide. Industrial scale demonstrations will also be shown to you, and this is just an example where Holcim has placed some of the concrete down with this wind turbine blade waste. If we go to the next slides, we can also ask ourselves which is the environmental and economic performance of this waste, and is it viable? And if we go to the next slide, it's ongoing, but we are happy to tell you that today we'll have the first results on this. So tune in into the rest of the webinar. So as a summary, we have mechanical recycling of end-of-life wind turbine blade waste and showing very promising results in producing demonstration construction materials. A demonstration plant is soon to be operational again. Maybe some updates will be needed here. Cementitious construction materials showed the highest technical performance. Several industrial scale tests have been carried out and are planned. And the project is approaching the end in December 2026. So if you want to hear more about it, please do not hesitate to contact us all that we are presenting today. So moving on, we have the webinar structure. I don't know if you want to take over here, Haris.
Yes, Anna, thanks a lot for your presentation. So this slide summarizes a little bit of the key products that we will share with you today, as we have a flow from the different treatment methods that we have applied for the wind turbine blade waste. Then we turn it into products. We have 4 different cases which have been tested in a lab scale, including polymer-based composites, lightweight aggregates, asphalt, and fiber-reinforced cement-based composites. So these are the 4 axes where we're gonna hear the presentations later on different aspects like application, synthesis process, and performance against virgin case concepts will be analyzed. And we have the industrial scale skeleton where we see how these products, these concepts leave the lab environment and can be transferred successfully into a big scale, large scale applications under the same concepts. A little bit again on the agenda, we've done the introduction, so I think to gain some time, I don't know if there's any questions, you can raise your hands. And we can at distinct timings the floor to you, but I think we need to speed up a little bit, so I'll pass on the floor to Dionysis and Maria from NTUA to present us the recycling routes and characterization of wind turbine blade wastes.
Hi, Haris. Hello, everyone. It's a pleasure to present you some of our activities today. Very briefly, I know we're a bit late, so moving on the next slide. As Anna already mentioned, we focus on the 3 R's of reuse, repurpose, and recycling, with the end goal of decreasing the landfill disposal by 90% until 2030. This is our goal. But in my presentation, I will briefly share with you our recycling methodologies. So if we move on the next slide, we will see that we have 3 different categories: the mechanical, thermal, and chemical recycling. For the mechanical recycling, we can see some more info on the next slide. As Anna already said, we used some large industrial scale shredders to break down the quite large wind turbine blades into smaller fragments. This was performed by PreZero initially, and then they were distributed to our project partners. Subsequently, TUV made this characterization, this different classification based on the different fractions per particle size, which was very useful for us because the smaller particles that you can see on the bottom of your screen were used subsequently in the new products that we developed, while the larger particles were used for the chemical and the thermal recycling due to size limitations. On the next slide, Paris, before we move to the chemical and thermal recycling, it was necessary to identify the composition of the waste, which is something very important to decide on the parameters and the solvents that we are going to use. And we took advantage of some analytic characterization methods like FTIR, for example, where we identified that wind turbine blades composites were mostly made out of unsaturated polyester resin. Also on the next slide, we can see the thermogravimetric analysis that we performed in order to quantify the amount of resin that these composites had in their composition. So we can see that it's almost 50%. This was important to know how efficient our methods were. Very well, on the next slide, Harris, you can see some of our parameters and equipment we use for the thermal recycling. We take advantage of some horizontal furnaces that we have with a tubular diameter, where we load the big fractions, as I mentioned before, and taking advantage of high temperature and argon, nitrogen, atmosphere, we pyrolyze our fibers, our composites, to receive the pyrolyzed GFRPs, and subsequently with the post-pyrolysis method, in order to remove any residues from the fiber surface, we reclaim the glass fibers, as you can see on the bottom of the slide, and how the micrography looks after an SEM image. On the next slide, we can see the updates from the chemical recycling. This is a high pressure temperature reactor that we used, 4 liter. Again, the big fractions were loaded inside the reactor, along with different solvents, water or acetone, in high pressures and temperatures, and again some characterization techniques to assess the properties of the fibers after the process. Very clean fibers for both cases. On the last slide, I think Harris also mentioned a few stuff, but here is the different products and materials that we used and how we use them, from which recycling routes. So for the mechanical, from the chemical and the thermal, and on the right side of your slide, you can see, for example, as we use them as fiber reinforcement, or CSM, or fine aggregates, coarse aggregates. For the chemical and thermal, mostly as fiber reinforcement, since we can receive clean fibers, while for the mechanical, we get the full composite after this process. So we don't separate resin from the fiber like we do with the chemical and thermal, and that was the main difference among the 3 different methods. That's all from our side, I think, Harris. So thank you very much for listening to us, and I think next we are going to see the products.
Yeah. Thank you, Dionysis. Again, everyone who's got a question, you can raise your hands, and we'll pass the floor to you. So after the introduction and the different routes that Dionysus explained, we go to the second phase of the presentation, which is about the product. So we see what the processes that will lead to handle this waste, now how these processes are translated and transferred into applications. And the first application, the first product we're going to see will be presented by Shashank from TUE. And Shashank, the floor is yours.
Thank you, Harris. Hello, everyone. I'm glad to present my results about the polymer composite made from wind turbine blade waste. Harris, can you go to the next one? So, as my colleague Dionys mentioned, we also make use of mechanically recycled wind turbine blade waste to come up with different polymer composites. So the first question comes to our mind is, can we recycle these waste coming from wind turbine blades into new polymer composites? To be very specific, can we combine this waste with polypropylene polymer matrix? So the answer is yes, we can actually do that, and we have successfully combined these two materials, and we have come up with a new um, composite material which is made of these two materials. Harris, can you go to the next one? So in order to produce these specimens, we also have to follow certain procedures in order to get the material with higher properties. So for that, as you can see on the screen, first we sieved the material which we received from one of our project partners, that is PreZero, and made sure we have the fibrous materials which can be used in the polymer composite as reinforcement material. So at first, we extruded the material by combining both virgin polypropylene and the shredded wind turbine blade waste. In the extrusion process, as you can see, we have used the temperature range of around 180 to 200 degrees Celsius. After which we also made use of injection molding to produce all sort of specimens with different compositions. And once we produced the specimens, we also wanted to characterize these specimens for different properties. Um, so we did the thermal properties, we analyzed thermal properties, mechanical and other characteristics for these specimens. But the next question comes is how to make it more circular. So the answer is yes. As you can see, it is reprocessing of these secondary composites. So as you all know, these days people are just combining the waste material in polymer matrix and just call it as a recycled composites. But our question was to analyze how many cycles these composites can be used or can be made use of. So for that purpose, we also investigated how reprocessing of these secondary composites will work on the new polypropylene composites. For that, we also shredded the specimens which were produced from these materials and then re-extruded the material, and also we did the injection molding. So this cycle went up to around 3 cycles. So now you must be wondering why we need to do the reprocessing of such composites when we actually get materials for cheaper prices. Harris, next one. Yeah. So to answer that, no. Can you go to the previous one? Sorry. Yeah. To answer that question, we also need to consider certain aspects which might affect these composites. So, for example, every polymer composite production will consist of, will consume around 100 111 megajoules per kilogram of energy, which is also the key parameter when it comes to polymer composite production. And also, we also need to consider the embodied energy of the glass fiber material itself. For example, the glass fiber material coming out of wind turbine blade waste will also consist of certain amount of embodied energy, which we also need to take into picture. Uh, the positive thing here is that the energy consumption during mechanical recycling is hardly zero point 0.1 to 4.8 megajoules per kilogram, which is almost 10 times lower than the actual polymer composite production. So going forward, Harris, next one. So going forward, we also want to know whether these specimens can be scaled up to different products for different applications. So as you can see, it is possible to scale up these specimens or the compositions into different materials for different applications. For example, this polymer composite can be used for exterior cladding panels or ceiling panels, decking boards, street and outdoor furniture. So these are the potential applications of these materials, which also has various advantages. For example, since we are talking about polymer composites, the main advantage of such materials is that it lightweightedness. So yeah, it is one of the advantages. And also, since I'm also making use of polypropylene, which is the recyclable thermoplastic material, which can be recycled up to 3 cycles. So you can use the same material for 3 cycles. You can recycle it multiple times. And also, as you all know, polymer composites is also a corrosion-free material, which is easier to fabricate and install. But having said that, we also need to look up certain disadvantages or further tests which we need to do when it comes to the fire performance of these components. And also, since some of the applications will have UV exposure to these materials, we also need to assess the UV weathering of these components. And also, again, we also need to make sure these components um, are adhered to the building code compliance. Harris next. Yeah. And now the question is, do they actually perform similar to virgin composites? So the next one. Yeah. So when we assessed these recycled composites, and also we compared these results with the virgin composites, and it was, I mean, we actually were surprised because after the first cycle, when we produced the specimens with the different compositions, the composition with 50% of wind turbine blade waste achieved almost around 86% tensile strength compared to the virgin glass fiber polypropylene composite. When we actually reprocessed it, the tensile strength actually increased to around 98% at the end of third cycle, which proves that this composite material performs really well in comparison to virgin composites, um, which also has good flexural performance. And also, we also wanted to assess the thermal performance of these materials, where we found out that the recycled materials coming from wind turbine blade waste actually helps the composite to have good thermal stability. That is, the degradation temperature has actually increased by around 5 to 12 degrees Celsius for these recycled composites. And on the other hand, also the crystallinity of the material also matters the most, because we are dealing with polypropylene material, which is a semi-crystalline material. So when we assessed the crystallinity of these materials, we understood that there was a huge increment in the crystallinity index of these materials, where it actually went up to around 80%. And also, there was a huge improvement in the crystallization temperature compared to pure polypropylene or virgin glass fiber composites. For example, the crystallization temperature of the recycled composites were increased up to around 5 to 6 degrees Celsius, which will eventually um, decrease or lowers the cycle time or the melting time of the material. And also, on the other hand, the material fluidity or the melt flow rate of the material also increased when we started increasing the amount of waste wind turbine blade. Which this particular material fluidity will also helps in the injection molding of these specimens. For example, if we want to scale up these products, then this is the most important parameter which we also need to look into. And also, lastly, we also need to look up the potential to substitute the virgin materials. So here in this particular composite material, it is possible to substitute almost around 10 to 15 weight percentage of virgin glass fibers with shredded wind turbine blade waste. And next one, Harris, please. And now we also have another question, that is, what are the actual benefits of these recycled polymer composites? So there are two benefits. That is, one is environmental benefit and the other one is economical benefit. For example, in environmental benefit, there are majorly we are actually reducing the landfilling and incineration of these wind turbine blade waste, and also this has actual potential to be reused or recycled into new polymer composites, which eventually reduces the non-biodegradable waste which gets arised because of these wind turbine blades. And yeah, as I mentioned earlier, it can also reduce the virgin material extraction, because as I told you earlier, it can actually substitute virgin glass fibers by around 10 to 15%. So this is also one of the environmental benefit. And coming to the economical part, the recycling industry is actually growing. So which eventually paves the way for these new polymer composites, and also which in turn gives more jobs to people in the recycling sector. And also, due to the usage of recycled materials in the products, there is also a huge potential for the reduction of these composite materials. So yeah, next one, Harris. So yeah, this is all about the polymer composites which we produced in this BLADES2BUILD project. Yeah, and also, yeah, you can click on this QR server now.
Thank you, Shashank, for a really nice presentation and very interesting. So now we can get a quick round of questions. If someone would like to ask Shashank about the product he has been developing, and
please go to the QRs.
Exactly.
There are 3 questions for you to answer for the polymer composites that we have seen from Shashank.
We go to the second case where Jaren from TUE is going to present about a potential of how we can also use this material on another direction on a non-polymer based composite product. So Jaren, floor is yours.
Hi, Haris, thank you. Hello, I am Ceren, a PhD candidate from TU Eindhoven. I will present about the production of cold-bonded aggregates using wind turbine blades. Haris, I just want to say that several slides contain some animations, so please continue clicking to reveal all the content. Thank you.
Very good note. Yeah, I'll do that, Jaren, to speed up.
Thank you. So here I would like to mention about the shredded wind blade waste. It is explained previously. This is a method instead of landfilling. So this material we received from our partner PreZero, which contains almost 40% of the powder-like, and the remaining part is, as you see, fiber-like materials, which is very heterogeneous in size and shape, also on the fibers. They have problems on their surface. Their surface has a lot of flaws. So here is a summary. It is a material that consists of glass fiber reinforced polymer, and it has powder-like and fiber-like particles in it. It has a low density and high water absorption, not because of the material is hydrophilic. It is actually quite hydrophobic, but the water absorption is happened because of the surface irregularities. And it has epoxy and also inorganic content. So the concrete industry has a potential to use this material, either sorting and using as a reinforcement and replacement for the powder and fiber morphologies. However, high incorporation levels of these very heterogeneous material, it still remains challenging. Yeah, please go to the next slide. Yeah, I would like to discuss a little bit of concrete, why it is challenging to incorporate these materials. So for concrete, this is a must to have aggregates, coarse and fine, for the classical concrete, I mean, and the powder, which is usually the binder and the microfiller and water. In addition to that, according to the purposes, we can add fibers, several chemical admixture, mineral additives, and so many other different purpose-serving elements into concrete. So, as it's mentioned before, this wind blade waste can be used replacing the concrete elements or as a fiber reinforcement, but it has some benefits and setbacks of both. So to be able to do that, first, we need to sort the material according to its morphology. Not only its size, but also its morphology. Secondly, of course, we have to sort it according to its size. Because of this material has a very low surface energy, they tend to create clusters when you try to sort them. So it is really hard to do sieving to sort them. So it is really hard to separate. And also inside of the concrete or mortar, if you replace a higher dosages, it is usually end with losing stiffness and strength, and it creates lower and weaker interfacial zone. And also, of course, because of the cluster formation, as I mentioned, there is a workability loss. On the other hand, when we do the reinforcement, of course, usually in most of the cases, we see some improvement in the bending properties. However, because of the fibers are not uniform and different, even though you sort them, there is a challenge in repeatability of these results and predictability of these good results. And also, again, because of the interlocking, there is a workability loss. And again, it is really hard to sort clean fiber fraction in this very heterogeneous waste stream. And on the other hand, I would like to discuss about the sustainability aspect. If you would like to use this waste material into the concrete, we also have to consider about the amount that we can put into the concrete. So usually the aggregates are the larger fractions inside of the concrete, approximately taken 65 to 70% of the total concrete volume. However, we can only put usually it is limited to maximum of 2% of concrete volume to add the fiber reinforcement. Even in some countries, it's even lower. So that focusing in the replacements concept and in particular aggregate replacement can allow us to put higher dosages of wind blade waste. But how? So if you can go to the next slide. So if we can create granular materials which is repeatable and more aggregate like particles from this very heterogeneous waste, then we can solve so many problems that is caused by the heterogeneity of the material. If you continue, the way to do it, there are several methods to create artificial aggregates, but the lower energy consumption method is the cold bonding pelletization. What is this? It requires a pelletizer, the waste material, the binder, which I use cement, but other binder can also be used, water, and also the curing after the pelletization, which we use the moisture curing. I have selected 3 different size fractions. One of them is powder rich, one of them is fiber rich, and the other of them is almost 50-50 fiber to powder. And also I used 3 different cement dosages. The problem of the pelletization is usually the pelletization is a method to create pellets or so-called artificial aggregates from the hydrophilic materials. However, since this waste material is quite hydrophobic, we needed to develop an engineered pelletization process to have strong aggregates. Yeah, thank you. Okay, this is the particle size distribution of the raw material. As I mentioned, different size fractions I have used for the aggregate production, which is X, Y, and Z, and also the cement. And this is the, sorry, can you go back?
Yeah,
once
sorry.
more? Thank you. And this is the particle size distribution of the produced aggregates, the abbreviation of the size fraction of waste, and the dosage of the cement. And here you can see the whole aggregates almost reach the point to be able to replace whole curve of the fine and coarse aggregates inside of the concrete. So it is possible to create the whole curve from fine aggregate to the coarse aggregate. Yeah. And these are some figures of the different artificial aggregates that we have achieved after the pelletization process. Okay, so if we would like to check the properties of the artificial aggregates, the most important and the most basic characterization property is the density. I have measured the apparent specific or skeleton density and the bulk density. The darker colors shows the apparent density and the line shows the bulk density. So according to the European standards, all of the produced aggregates are in the classification of the lightweight aggregate. And also, if we continue, there is another several important parameters for lightweight aggregates, which is water absorption and the porosity. Usually they are connected to each other. According to the literature, I also have compared my results with the other lightweight aggregates in use in the industry by the industry currently. I see that the water absorption and the porosity is in line with the artificial aggregates and the lightweight aggregates in use in the industry currently. Yeah. Okay, and some other property, when we discuss about the property, of course, the strength comes to mind. And for these artificial aggregates, the crushing strength is one important parameter. This is achieved by crushing one individual aggregate. In these graphs, the 15 different aggregates are tested, and those are the average values by recipe. And what we see that according to the used particle size of raw material, different types of aggregates were achieved. One of them is regular pelletization, and the other one is encapsulation. So both of them has different benefits, but it is obvious that if there is an encapsulation form, then the strength of the aggregate and also the water absorption and also the strength of the aggregate is increasing. There are some pictures of the cross section of the pellets. If you click one more, yeah, here is the regular pellet, and this is the encapsulation form. This whole the procedure is the same, but the only different thing is the size fraction of the selected size fraction of the waste. To assess more, we also put these aggregates inside of the mortar and test the mortar properties. We selected the best performing aggregates, which is Z30, and here is the recipe for the aggregates, recipe for the mortars that we have prepared. We replaced the 50% of the sand and 100 of the sand with these artificial aggregates. And there was a interesting result on workability. Here it is a reference mortar, and if you click one more, here it is the 100% replaced mortar. This when we replace the sand, and I just add this this image from one of my other study. This is if we add the wind turbine blade waste as it is in the sand replacement, so it usually creates a problem in the workability. This problem can be solved if we have more granular aggregates, as you can see. And also, if you can click once more, I would like to highlight the dose of the wind blade waste in this performance. So here it is 34% of total mass of the mortar coming from wind blade waste, while the poor workability has only 5% wind blade waste inside. Yeah. Also, we have some other properties of the mortar, just to compare it with the virgin case, the reference case. Of course, as expected, since the reference mortar is prepared with the sand, the river sand, it has a higher strength because there is no such high porosity in it. However, it is still comparable. When we have the 50% replacement, we have the strength approximately 30 megapascal, and we have if we have replaced 100%, we have 22 to 24 megapascal of the compressive strength, and the flexural strength almost remains stable. If we also, since the density of the mortar decreasing a lot, also we have discussed the specific strength, which shows a decrease as expected, but still we have acceptable level of strength. Also, we tested durability on ASR expansions because the waste has a lot of glass in it, and also we checked the drying shrinkage because the aggregates have a lot of porosity in it. When we check the alkali silica reaction possibility, we see that the aggregate artificial aggregate replaced mortars performed better than the reference because of the cement paste coating around the waste. And when we check the drying shrinkage, yeah, we see increase of the shrinkage with the increase of the dosage of aggregates. However, it is comparable I checked from the literature, and it is comparable with other artificial lightweight aggregates. Also, from the physical properties, we have checked the thermal conductivity because we are bringing some closed pores inside of the mortar. And we see improvement in thermal conductivity, so it has an insulation property. And if you click one more, please. Yeah. We also have checked the leaching according to the Dutch soil quality regulations, and we didn't see any risk on the leaching properties. Yes, if you click one more, Haris, yeah. Yeah, we have tested one batch leaching and there was no risk, yeah. And this, I'm happy to share that this method and this method to producing artificial aggregates and the aggregates themselves is patented in Netherlands. And yeah, I would like to also summarize the conclusions. And so it is a high value end-of-life solution for wind turbine blades. And it is also converting difficult composite waste into usable lightweight aggregates. Several use cases I will be listing now. So could be structural lightweight concrete with playing around to the pelletization process to increase its strength. Can be used in non-structural applications, can be used in thermal insulation applications, for green infrastructure, or sometimes for lightweight filling materials, prefabricated products, or also it has a benefit to transportation of the waste, which has a lot of dust. And also because it is very low energy consumption, because it's just cold bonded pelletization, it is easily scalable, and just humid curing, there is no heat or other curing methods. So, and also it allows us to use high amount of wind blade waste in itself of aggregates, or itself the product that aggregate is being put in, like concrete or mortar. Yeah, thank you. This is all from my side.
Excellent. Thank you, Turan. A very interesting approach, as well as Shashank showed us before. On the same structure, we can have a round of questions if you want to raise your hand. And of course, you're more than welcome to go and scan the QR code for this particular product and share your feedback. So 10 past 12. So I hope everyone is back after the coffee break. And we saw two interesting cases on how we can valorize end-of-life wind turbine blade in the previous two presentations. One case on synthesizing polymer-based composites for different applications, from cladding walls up to benches and stuff, and also how we can create aggregates which can be used into cement-based composites and allow a larger volume of incorporation into the material. So now we can pass on to our three product case study, and yeah, I need to welcome Tung to present it, and a special thanks to him because he's currently on holiday. So yeah, massive appreciation for your input, Tung, from all the consortium and personally. So floor is yours.
Yeah, thank you, Harris. Hopefully that you can hear me very well because the internet here is not very good, and maybe you can hear the motor noise because I'm staying in my parents' house and it's nearby the road, so in Hanoi.
It's
So
it's
it's no
perfect
one
so
here.
far. It's perfect
Okay.
so far. So you can continue.
Okay, thank you. So yes, I'm Duc Thung Dao, a research scientist from the Ho Chi Minh Innovation Center. We are based in Lyon, in France. We are involved in the BLADES2BUILD project to work more on the laboratory R&D and then also for the demonstration. So this is the first presentation that I would like to present to you, focusing on the way that we can find the application. So as Harris made a very well on the introduction, we try in different applications, and we try to scale up it in the demonstrations scenarios. So my presentation will focus on the transformation from the wind turbine blade waste to the circular construction materials, and then I will give some update from the asphalt. Next slide, please. So yes, here we are in the second step for the R&D roadmap of the project, like in the development of the circular building materials. For sure that we try to put as much as we can the wind turbine blade waste inside without any compromise in terms of behavior. So we talk about mechanical behavior, like you can see in the previous slides, but also on the durability before going to the other scan, like the demonstration and the user scan. So we are staying in the laboratory scan in this presentation. Please go to the next slide. So this is a very simple way to illustrate how we think about the circular innovation to recycle the wind turbine blade waste in the construction materials. We have on the left side hand the chart to see that yes, we can recycle the wind turbine blade waste in different applications, but there's own way the constraints between the value that we are going to create and the limit in terms of technological disruption. We would like to go to the cement-fired replacement. We would like to go to the dry mortar, the insulation, and so on. But the TRN of these technologies are still limited, 4, 5, I would say. And then we need to put a lot of money for the investments, so in the capex, that we can adapt the industrial production lines. Otherwise, in the other sense, in other direction, if we stay on the landfilling, on the co-processing, yes, the TRN are quite high today. We can scale up. We can go to the ring case, ring scale without any trouble. But the value that we are going to create is very low. So that's why we decide to work on the concrete and asphalt, which is the best compromise between the added value creation and then the technological disruption. And we base on what we can do today. So after 3 years of BLADES2BUILD project, today we can generate different raw materials that are ready to be integrated in different existing products. That you can see that we can produce clean recycled fibers by using the thermal and chemical transformation. But in other cases as well, we can produce the fines and the cost on fine aggregates with the mechanical transformation. And for the concrete application that I said previously, we use the fine and aggregate coming from the mechanical transformation for the upcoming development. So please move to the next slide, please. So here is the study that Asiana carried out during the project, and unfortunately, Amaya from Asiana, she left for holidays as well. So I've been presented on behalf of Amaya and Asiana part. So the idea is very simple. We got the fibers cleaned from the sunvoresist and pyroresist processes given by the NGUA 2 years before, with a residual content present at 1%, and Asiana tried to evaluate the feasibility and performance of the new asphalt recipe containing different type of clean recycled fibers. They follow the set of tests like the workability and the production in terms of void content. They follow the density and measurement void content, I say it, and then durability against the weighted image. So it's called the water sensibility. And for sure, they measured the modulus, so the elasticity of the asphalt according to the proper or to the normal way that they do to develop an asphalt recipe. So in the test, in the study, they put 1% of the fibers, and they try to benchmark with the traditional or the ordinary asphalt. So please go to the next slide where we can find more reasons. So the recipe that they they selected to the study is the AC16S. AC is asphalt concrete. 16 is the DMAX, so the maximum dimension of the aggregate, so 16 millimeters. S, I think, is about the semi-dense, is a type of the asphalt within the siliceous and limestone aggregate. They use the bitumen 50/70, so it's the hardest bitumen grade that usually used for the hot weather on the materials. So from the bitumen to aggregate were heated at 165 degrees Celsius, including the fibers, and they mix it by using the I think it's binary mixer that you can see in the pictures. Then they did on the list of the tests that I presented in the previous slides. In terms of behavior, we didn't see any difference in terms of density between the ordinary asphalt and then the asphalt with 1% of winter bean bed waste. In terms of void content, we have a little bit higher in terms of void content, but it's not like the concrete, because in the concrete we don't like the voids. In the asphalt we like the voids because the void is there to protect the volume change due to the thermal gradient between the seasons, to be sure that the bitumen can find the place then when it is melt by the increase of the temperature. So when we have the recipe of the asphalt, the first thing that we have to check is the void contents. And normally in the norm, they recommend from the 4 to 5 or 4 to 6% of avoid that can say that the asphalt is good enough. So here in our case, we have more void content than the ordinary asphalt. So it's a good side and it's totally accepted. They observed that the recycled fibers were very well integrated in the bituminous and matrix, that they didn't see any block of the fibers that stay locally in one area in the mixture. The fibers was also well coated by the binder, and there's no change or no difference in term density or in the void content that I showed to you. So the good promising reasons for the density and void content. Please go to the next slide, please. And then in terms of mechanical behavior, like here we talk about the stiffness. So stiffness is the elasticity modulus at fixed frequencies, and then the temperatures, I think it's about 15 hertz at 10 degrees Celsius of temperature, or 15 degrees of Celsius and 10 hertz. They see improvement in terms of stiffness, meaning that with 1% of wind turbine blade width, we have the stiffer asphalt at the same condition of testing compared to the ordinary asphalt. And they thought that thanks to the 1% of wind turbine blade width fibers, they got a reinforcement like the fibers in the concrete in this case. And this increase is very important, about 14 to 45% depending on the 5 fibers, because as I told before, they try 2 types of fibers given from pyrolysis or photoresist processes with different percentage. Here they don't put on the reasons, but the conclusions showed from 14 to 45. Okay. And then in terms of durability, they tried also the water sensibility test. So in a few words, like they have a set of samples that they conserve in the air, so in the controlled condition, and then a second set of samples they put it in the water, under the water, and then they get them out for 7 days or for 28 days, and they dip the compressive strength, or I don't know what kind of test here, and then they try to compare it. If the asphalt is in the air conservation condition or in the water conservation condition, what is the difference? And we see that yes, because of the water conservation, that the mechanical behavior of the asphalt reduced, but compared to the ordinary asphalt, where there was 9% of loss in terms of strength, in the new recipe with 1% of clean recycled fibers issued from the wind turbine blade waste, the loss is around 8%. I think from 9 to 8 is not so much, it's just in the standard deviation for the test studies, but it showed that the durability of the new recipe with the wind turbine blade waste is acceptable and is comparable to the ordinary asphalt. So by combining the density, so the mixing process, the density, the void content, the stiffness, and the durability, Ashana draw the conclusion like the own design mixtures meet the strictest Spanish road specifications, allowing their use for any Spanish roadway. So the conclusion is very clear and is very impactful in the way that the recipes are ready to be used if there is any opportunity where the asphalt will be used for new payment, they are ready to propose this. Unfortunately, we decide, or Asiana decide, that they don't want to go to the bigger scale in terms of demonstration. All the reasons they found here stayed in the laboratory scan, and they will find maybe opportunity outside the project in the future to make it brings in terms of payments. I think it's the last slide from my side. Please go ahead for the queer survey. Yes.
Thank you, Chung, a lot. In line with what we've done for the two previously presented products, we have a QR code where you can scan and share us your feedback. Where we'll start with our colleague Tao from DTU, who's going to present the mechanically shredded blade waste to be used as fiber reinforcement, and then Cynthia from RWTH will continue with presenting a similar topic using the chemically and thermally treated material as well. So, Tao, I think the floor is yours.
Hello, thank you, Haris, for the initiatives, and also thank you the previous colleagues in the presentation of all the usage of turbine blade waste. So here in Technical University of Denmark, we are kind of using these materials, the shredded turbine blade waste, as a fiber reinforcement in the mortar cases. So please next, Haris. And the project background is already presented. So we directly start with the pathway of using these materials in the cement-based composite. So we try to repurpose using the waste in the cement base as reinforcement or replacement. And the reinforcement case is just use the fibers as it is, as received the materials. So it is kind of mechanically treated. While we're using these materials may have the potential impacts some new materials design based on the cement chemistry and enabling the customized performance and new design of the grain binders or fiber reinforcement, and also enabling the efficient and the integrative use of this kind of complex solid waste. Please next. Here in DTU, we have two pathways as well, replacement or reinforcement. Replacement will not like describe it, but we use the sieve and crush the powders in the cement paste. And then as a fiber reinforcement, as we see the picture on the left, we do it in a mortar to test how the mechanical performance it is, flexural and compressive strength, and also further test on the shrinkage and alkali silicate reaction expansion on the mortar samples as well. Please next. And this fiber reinforcement pathway, we put the materials in the mortars, and then we cut the cubic materials to do the CT scanning to see how the materials distributed in the mortars. The left side is the distribution of the materials in the mortars. The right one is the pores and the fiber distribution in the mortar. It's kind of difficult to distinguish the pores and also the fibers, because the fibers from the blade waste contains between the resins and the glass fibers. The resins has relatively very low density, just like the pores. In the microcity, we can only identify from the shape of it instead of the density. Please, next one. And then how we kind of test it further on the mechanical property. When we first do the receive the materials, we sieve them into different particle size to see if the size effect on the fiber reinforcement performance, because we know that the shredded process of the turbine blade waste cannot guarantee a very homogeneous materials outcomes. So we sieve that to see if this size effect Okay, from the left side is the compressive strength, and the right side is the flexure strength. I think we have the title if you type on next. Oh, we don't have it, so previous one. And then we see the different size of the blade waist. So the W means turbine blade waist, and the numbering afterwards is the size of the blade waist. 0.063 is the 0.063 micrometer. 0.5 is 0.5 micrometer. 2 is 2 micrometer milliliter, not micro, and 8 is 8 millimeter. So we can see that from the compressive strength, they can help with very good compressive strength. And also the left is the flexure strength, as we know that if you do the fiber reinforcement, the flexure strengths are also kind of increased. From the both case, we know that at around 2 millimeters is a kind of very optimum performance by both case, whatever the compressive or the flexure strength. So next slide, please. Also, we also kind of do the different volume fraction instead of only the particle size of the fibers. We incorporated this turbine blade waist from 0.5 to 2 volume percentage in the mortar samples. For both cases, you can see that the compressive strength a little bit decreased because the materials put inside, they may have introduced some more porous, and they have some interfraction zones, weakness. So the compressive strength has a little bit decreased, but when we use the supercapacitor, they kind of eliminate this kind of negative effect of the fiber reinforcement. But on the right side, the fiber reinforcement of different volume fractions, we can see that when we have one volume percentage, they can help with the fiber reinforcement, whatever they have superplexicizer or not. Next slide, please. This is kind of comparison. If we have these materials, how does it compare to another materials? We investigated comparing with the literatures, have steel fiber, PVA fiber, and basalt fibers. Our wind turbine blade fibers here is 0.5 volume percentage. They shows kind of comparative reinforcement cases. We know that steel fibers are very good, but in some cases we are kind of a little bit higher than the steel fiber as well. But in general, they are comparative to all the other fiber reinforcement materials as well. Next, please. So the final take-home message is like the turbine blade waste can enter in the cement-based material through the reinforcement and replacement pathways as we presented. And the reinforcement evidence are kind of proved by the micro CD and the SCMs. We know that when these fiber distribute in the mortars and interact with the pores and matrix, they can kind of help with fiber with the mortar flexure strength specifically. In the compressive strength cases, sometimes when we do the compressive testings on that, the fiber can also bridging the cracks. So in some cases of small fibers, they can also help with the compressive strength. And we also test the different particle size and different volume fractions of that. So the strength gains depends on the fiber size and volume fractions, and also the superplexicizer uses or not. The fiber size are better within 2 to 8 millimeter. The volume size, volume fraction are better at around 1 volume percentage, and superplexicizer help with the performance of the general cases. So the design implication in the final application will focus on optimizing the size, dosage distribution, and the biochemistry to balance the final mechanical performance, workability, durability, and maybe the circularity of using these materials. Okay, thanks. I may pass the floor to the Cynthia.
Thank you, Chao. Cynthia, the floor is yours.
Okay, thank you very much. So hello, everyone. I'm Cynthia from the RWTH in Aachen. I work at the Institute of Building Materials Research. And I just wanted to briefly present some results that we have achieved in this project so far. So I would like continue with what Chao has previously presented. So we at Aachen, we received mechanically treated with turbine blade waste materials from different companies or different preparators, I would say. So in the slide, you see, or you should observe different fractions from these mechanically treated, for example, fibers. And they do differ in one's the density, but as also in the Loy content. The higher the Loy content it is, the lower the density naturally. But we do see some major differences here. Now, in the slides later, I will only present as a comparison the results from the mechanically treated wind turbine blade waste from the B9710. So if you please go to the next slide, that's why I have it highlighted. So now we see some pictures of how the chemically treated fibers look like. These are exactly the chemically treated fibers that were provided by our colleagues from Greece. Also here, different batches do deliver minimal differences in the Loy content and actually not even really measurable, more or less the same density. If we go to the next slide, please, then we will see the thermally treated fibers, which were also provided from our colleagues from Greece. So just looking at the pictures, you will see directly the sample, the 8660, you see something black. Okay, so it does differ. This is measurable in the Loy content as well. And just keep this in mind because, we integrated these fibers into our standard mortar mixtures, and then you will see that there are some variations. And this slightly has to do a little bit with the materials that we received. So everything that we received here at EBAC was produced one-on-one exactly that way. So we did not do any further processing of these materials in any way. So if we go to the next slide, please, and you will see the mixture that we worked with. We based our results or our studies from the standard mortar mixture according to the DIN 196.1. Just to keep it simple, we also did concrete tests, but I think this is something where we can compare our results from by adding these wind turbine blade waste with other supplementary cementitious materials and stuff like that. So, so we added 8 grams of fiber per mixture, which is more or less 1.8 mass percent of the based on the binder content to our mixture. So we have a reference mixture. That means we have one without any wind turbine blade waste. Then we have the mechanically treated wind turbine blade, just one of them. And then we have our thermally treated ones and the chemically treated ones. So I tried doing the slides in a way that all these colors will pop up the same for the next slides. Just to refresh on what we saw earlier, this comparison of the density and the difference on loss of ignitions, it's also depicted on the diagram on the right-hand side. So if we go to the next slide, please, and you will see the results of the fresh mortar properties. So what we did is, for once we did the flow table spread, which is the consistency measurement. We did some air content measurement values, and as well, we also did the measurement on the density. So just starting from the right-hand side, we will see that we don't have actually any change, measurable change in the density. With this small amount of fibers, this is actually more or less something that we thought shouldn't change that much. We do have, however, a slight change in the air content in this one specific sample, the 9659 sample, which is a thermally treated fiber. Remember, that's the one that was black a little bit on the surface. So there is something definitely happening there, a little bit different. So then we did see a slight difference on the left-hand side diagram from the consistency. We did see a small reducement of the consistency. However, this is something with the way our colleagues in DTU are handling it is with the use of PCEs or a super plasticizer, something that we can more or less from a concrete technology point of view easily change. But since this was not our focus, we just left the mixtures the way it was. So if we go to the next slide, we will see what happens with the hardened concrete properties. So please just try to focus on the left-hand side with the flexural strength. Look for the gray line, and you will see that this gray line without the fibers or the wind turbine blade waste has actually the lowest performance. Everything with the added fibers has the higher performance. Okay, so more or less, you will see a very similar trend concerning the compressive strength. However, we do have one sample also here, the thermally treated one, because this thermally treated ones, they are sometimes a little bit, do react a little bit different. So you see that on the color, the blue color lines, the chemically treated ones is in every single case much better than without any fibers. Okay, so I would say just on based on these values, we do see that we have an improved mechanical performance just by adding a very small amount of wind turbine blade waste into our mixture. So if we go to the next slide, I have picked extra the data on the just like the flexural and the compressive strength, which is just based on the 28 days. So we actually did see all these values before in the slide before this, but I think it's sometimes easier just to concentrate on one specific date. So we do see again here that we did improve our flexural strength with every addition of the wind turbine blade waste. With the compressive strength, like I said, we do have some smaller difficulties concerning the thermally treated ones. These do tend to differ a little bit more. You also see this on the standard deviation of these samples. But more or less, like I said, we do have an exceeding of the compressive and flexural strength by adding the wind turbine blade waste. So if we go to the next slide, please. Then we come directly to our very small conclusion that we do have with the thermally treated ones and the chemically treated ones definitely the smallest amount of the loss on ignition content. This is normally smaller than 0.3. Remember, when talking about the mechanically treated ones, we had values of 30-40%. And thus we have a higher density. We did see that all of these fibrous mixtures, or the mixtures including the wind turbine blade waste, we had a very good early strength development with no negative impact of the wind turbine blades into the cement hydration. And we did, however, see small differences talking about the thermally treated ones. How in the chemically treated wind turbine blade waste worked perfectly fine. Okay, so I think this also sums up what the colleagues from DTU were talking about, the possibility of using the wind turbine blade waste as a fiber in a mortar. It is also definitely possible to integrate the chemically treated fibers. The thermally would probably also be possible. However, I think it is probably a little bit more work to be done on this aspect just to keep the same quality of the wind turbine blade waste. Okay, so I'm happy to answer any questions you have.
Many thanks to Cynthia and Ta for an excellent presentation and for distributing these very nice figures on a comparative basis. We go on the same route as before, so you can scan the QR code here, and in parallel you can raise your hand or write it in the chat about the questions you may want to ask the presenters. And then it's time for Victor and Tung to present the first part of this upscaled case, and after we see like the first large scale results and large scale applications, David and Rose will follow with an LCA analysis on the product. So we go out, as I said, from the lab case to a more upscaled version of how we can immediately valorize this waste into real applications, so real world applications. So yeah, is Victor or who's
I'm here.
present?
Can you hear me? Yes.
Yes, Victor.
Yeah, good day to everybody. It's really a pleasure to be here. So I'm letting Toon to be on holiday, so I will do the presentation on this. So my name is Victor Pacheco. I'm the Innovation Process Manager of the Holcim Innovation Center. And we go already to the next trial. And as you very well said, we really wanted like this. This doesn't stay as a kind of lab exercise. We really wanted to go to trials. We really wanted to show that this material can really be multiplied. And this is what we try to do with two big industrial trials, the biggest that we have done in this project now. Perhaps we will be able to do even a bigger one by the end of the year, but let's see. So if we start with the one which is the biggest that we did until now, Maria, you can go to the next slide, please. Yeah. So how do we do this big trial? So we started obviously getting the material, as you know, and it has been presenting here by all my colleagues from the project. So we treat the all turbine blades to produce what we call recycling aggregate. And in these specific trials, we did it together with PreZero, also a partner here in the consortium. And we were able to produce in this process 0.10 millimeters and 0.40 millimeters aggregate. And for that, together with Holcim Spain and us, the Holcim Innovation Center from Holcim, we were able to do a kind of a special formulation where, and you will see also in the next slide, we did a mix of the recycling fibers from the wind turbine blade and construction demolition materials to, under the CoCycle brand from Holcim, reach 10% of recycling material in the concrete. Maria, you go to the next, please. And this is actually what we did. So we did the concrete with 10% of a mix of construction demolition material plus wind blades. And we wanted to prove also that the workability and the strength was actually the same than, let's say, a normal concrete. And we were able to do this due to our, let's say, Holcim mix design expertise. You go to the next, Maria. And here were the demonstrators. So we wanted to be very symbolic, I would say. So together with Endesa, you know, Endesa is one of the biggest energy companies in Spain. It's part of the group Enel in Italy. So we choose one of the wind farms in Aldea Vieja, which is north Madrid. And also, this time we not only wanted to do circularity. So this concrete didn't have only, let's say, 10% recycling material. Also, we wanted to go down in CO2. So we were able to design a concrete called EcoPack, which is our brand of low carbon concrete, where it has at least 30% less CO2 reduction. And this one, as you can see in the picture, and we will go to the video now, it was the platform of the recycling center from the wind farm. And Maria, I think we have time, so we could go to the video, please. I cannot hear the sound, Maria, but anyways, what you see here is one of our Holcim labs where we were preparing the mix design. So it's the concrete lab from Holcim, Spain. And there we are, let's say, where we did the magic, really fine, develop the formula where we could develop this concrete, as I said, with 10% construction demolition material mixed with, you can see there the blades, and also let's say the CO2 reduction. And yeah, here we're also talking about let's say our EcoCycle brand, where I mean, in Holcim for us is really important circularity, so we try to, let's say, to put products in the market with I would call it a brand label. Our EcoCycle label is everything that has at least 10% of construction demolition, 10% of construction demolition material inside. Yeah, and this is actually me explaining exactly what we are doing, because in Holcim strategy in 2024 we already recycling 6.5 million tons, as you see, and we have a goal of reach 20 millions by 2030 of construction demolition waste. So this is why we are really happy to be part of this consortium, the Place to Build. And this is Francisco Valle from Endesa, and where he's playing, you can read also like that this can be really a solution for the wind turbine blade recycling. And this, you can see how we have to move like the ready mix track to the top of the mountains. And this was exactly the moment we were doing the trial. You can see the concrete going down for this platform of the recycling center of the wind farm. And there where we are putting the concrete. As I said, it's the first in Europe, but also I would say perhaps probably also in the world, where you have a wind farm which has been using concrete with minus 30% CO2 and on top wind blade waste. Yeah, I think this is basically the end, Maria. So we are extremely really proud of this trial that we were able to do with Endesa. But and that was the biggest we have done now until the project. But it was not the last, the only one we did together with Acciona, and we did a demonstrator in the R&D center in Madrid, which was a kind of it was a road. In this concrete, we incorporate 11% of recycling content. So we did the same. We did a mix of construction demolition waste, recycling aggregate, and wind blade to reach 11%, thanks to the EcoCycle technology from Holcim. But we really wanted to go further, also in the topic of CO2. So we try a special cement, a cement called EcoPlanet from Holcim also, that we were able to reduce the emissions 49%. So we really wanted to go big here in this demonstrator with Acciona in terms of not only circularity, but also CO2 reduction. And actually, this demonstrator won an award from the European Concrete Road Association in Brussels, and I think Tun from Holcim and Amaya from, no, it was not Tun, another colleague from Holcim and Amaya from Acciona went to pick up the prize. Yeah, and I think the next one, I think the last one. Yeah, and so the last trial, so this is basically the third one that we did, big industrial trial. So the first with Endesa, second and the third with Acciona was a kind of another demonstrator of a mix of EcoCycle, EcoPlanet technology. And you can see the other one was a kind of rod. This was a kind of columns, and also was in cooperation with Perry. And the target was like we really could, let's say, make this industrial. We could really multiply all this technology from lab to, let's say, to industrial scale. And yeah, I think this is basically all from my side. To wrap up, I mean, we did a huge effort in terms of circularity with this project, and also we demonstrate that we can even do it together with a CO2 reduction. So we are really proud of all this trial. We are even trying to do more by the end of the year, and I think we can say as a conclusion that yes, this material can be used in construction material and can be really multiplied at industrial scale. Thank you so much.
Many thanks, Victor. And yeah, nice to see like the transition from lab to real life applications. And as a follow-up of this very nice and interesting industrial case application, we will also, as in our last presentation for today, we will also present a little bit more in-depth analysis, life cycle analysis on how this material could be in line and in compliance with modern requirements in terms of construction industry. So for this reason, Rose, I guess, from RWTH is going to present us the life cycle assessment of a specific type of concrete that has been used, as we saw before, and has used for synthesis wind turbine blade waste. So
hi everyone. Yeah, so you can get me hopefully. So nice to be here and to be able to present also this part of the results of the BLADES2BUILD project. So I'm presenting on behalf of RWTH, and my colleague David Heise is also with me. We will be focusing on environmental sustainability and applied, especially considering the industrial scale product, which was also presented. Part of it was presented above, but I want to also stress the fact that we will be considering data related just to the wind turbine blades that were used in these industrial scale products. So next slide, thank you. So let's talk about sustainability. What is sustainability? So we want to meet the needs of the present generation without compromising future generations to meet their needs. And when we have needs there, we want to incorporate the 3 dimensions of sustainability. So increasing economic growth, as we want all of us, organizations and companies, I want to increase their growth, the GDP, but looking at the planet, which is also the source of the resources we need for our economic growth, and also being careful not to impact the people, so the social dimension. So we look at the 3 dimensions of sustainability and considering a long-term view. These are the innovative aspects of this definition, because everyone talks about sustainability, but it is, we have to bear in mind these three aspects, and also the fact that it is not just declaring or claiming that something is sustainable. We need to measure the sustainability. Next slide, thank you. So we, in measuring sustainability, it's important to have a life cycle thinking approach. So when you have a product, you need to look at the impact on the three dimensions coming from the different stages. So the life cycle stages of that product. So you will have the extraction of the raw materials, you have design, you have the manufacturing of the product, distribution, the use, and end of life of it. So what happens when that product becomes a waste? So that's the end of life, and that is also what we will be addressing in this part of the slide. But it is also a very important aspect of the BLADES2BUILD project. Yes, next, please. So how do we get to measure the sustainability performance? We have, for these three dimensions, we have already the ISO and methodology on how to measure sustainability and not just claim it, and taking into consideration the life cycle perspective, as we introduced earlier, from the extraction of the raw materials to the manufacturing, to the use, and also the end of life. For this, the purpose of this project, we are going to focus on the life cycle assessment, which is the environmental performance of sustainability. And that is what we try to check if our wind turbine blades waste incorporated in the manufacturing of concrete has a higher or a lower impact. Next slide, thank you. So what is this life cycle assessment? We need to compile and evaluate all the inputs and outputs, and also calculate the potential environmental impacts that occur all through the life cycle of the product. And in the case of concrete, can you go to the, can you click more? Okay. So there is a model. You have to model the whole system, all the unit processes in that is involved in the product or in supplying the product, and collect all the inputs and outputs, so material flows, energy flows, waste, everything that is used into the manufacturing, into the extraction, but everything that also comes out of it. All of these inputs and outputs have environmental impacts that have been characterized, and that characterization, through characterization factors, are used in the impact assessment phase. So you have 4 steps of life cycle assessment: the goal and scope inventory, where you collect all the data; the impact assessment, where you assess really what the impacts are, and interpretation. Just a few words on the inventory. So you can have generic data, which you have from secondary databases, but in our project, we collected primary data, which means this is data, input and output data, that is specifically related to our product. And this distinguishes the result from the other results of concrete-related LCA. Please, next slide. So we are now addressing the waste problem. We will be having massive generation of waste from the composite materials related to the wind turbine blades, and we want to see how we can support the circularity of this material. And we started with the mechanical recycling of this wind turbine blade waste. And we try to use even the input and output data, which we got also from PreZero, one of our partners of this consortium. Please, the next slide. And all of this information was embedded in what we call the life cycle assessment decision-making tool, because an important aspect of life cycle of LCA is to guide the design, development, and also use and end of life of products. So we can understand where the highest impact is and try to reduce it as much as possible. And here we're talking about environmental impacts. How can we include or embed the wind turbine blade waste into concrete production, and in order to valorize as much as possible these waste, but taking into consideration the necessity to reduce environmental impact. So that is our question, and that is what LCA wants to help us in resolving. Next slide. So our goal here is to assess the environmental performance of first the mechanical shredded wind turbine blades, which is already at a high industrial scale. The readiness level is 7, and we have to follow the LCA methodology, and we have the data that is provided from PreZero, our partner, and for 1 ton of wind turbine blade waste shredded at their facility. Yes, please. More, yeah. So we model the system. So it starts from the gate of the PreZero and until when everything goes out of their gate. So the shredded composite, which has been mechanically recycled. And for each of those processes, you can see there, we had to collect specific data on diesel consumption, electricity, all the oil, and also antifreeze substances that were used, and also collect information on which type of outputs there were. So residues of dangerous substances or wood or other plastic containers had to be quantified and also characterized in the LCA model. Next slide, please. Coming to our results for the shredded composites, so the mechanical recycling, we want to see where the hotspots are. So the LCA result helps us to understand which of these inputs and outputs contributed the most to the environmental impacts, which you see below. So when we talk about environmental impacts, it's not just climate change. It's not just CO2 emissions. And it is first, if you talk about CO2 emissions, those are just emissions and not impacts. But here we talk about climate change, which is measured as a CO2 equivalent. So you can see climate change, you can see acidification. You also have water use, ozone depletion. All of these are environmental impacts that can be measured using LCA. And here you see for the shredded composite, can you go to the next slide, please? You have higher comparing with the virgin gravel, because that substitutes the virgin gravel. You have higher impacts for the virgin gravel. But then we need to bear in mind the life cycle perspective. So it's not only about the gravel, it's about the final use of it. So it's about the final use of the wind turbine blade with shredded composite. And we can see that in the next slide. So when we substitute, exactly. So we are now moving to another level, the concrete, and collecting all the information, inputs and outputs in concrete production, the cement type, the sand and gravel, and also the recycled aggregates, together with a wind turbine with shredded composite, plasticizers, super plasticizers, the water and tap which is used, tap water which is used. We collected specific information, especially for the industrial scale that was carried out by Holcim and also Acciona, to understand what is the ultimate contribution to these from these wind turbine blades. Can you please go ahead? And here we can see that we have really not much difference in the impacts. This is a different picture from what we saw when we just aimed at the mechanically shredded wind turbine blade waste. So here it's about the application. So we use it in concrete. So when you have it in concrete, you have recyclability or circularity without increasing much the impact. As you can see also in the next slide, we have just up to just 0.6% of increase of the impact. And this is mostly for the land use and land use change or water use aspects. So here we talk more about how circular our wind turbine blades from the mechanically shredded process can be if we include it in a final product, such as cement and such as concrete, also at industrial scale. Takeaways, last slide, I think it should be, yes. So mechanically shredded pathways, yeah, they are viable at industrial level and also an alternative to landfill disposal. Next, can you just go to the okay. And you have at material level, you can have higher, but then when you go more into the applications level, you have less impact. So they are equivalent. And finally, all of these also, what was done is based on a conservative baseline. So much information also is needed to corroborate this and also give us a way forward for other higher large scale applications. And that's it from my side. Thank you.
Many thanks, Rose. So this was the last presentation for today. And as we did with the previous ones, you can still do the QR survey. Here, a little bit of summary. So we saw again the 3 different treatment routes that we can use in order to start the process for valorizing end-of-life wind turbine blades. So we saw the mechanically shredded way, which is the first route, then the solvolysis road, which is a chemical treatment, and the pyrolysis road, which is a pathway, which is a thermal treatment. And then after treating this material, we saw different applications which range from lab scale to industrial scale. So we saw how we can use this mechanically shredded material to prepare new polymer-based composites that can be used in decking, in roofing, in facade cladding. We show from Shashank that this material can be not only like efficient, but also can be recycled 2 or 3 times and give still quite confident results. We saw the lightweight aggregates case from Jeren, where it's a very novel application on how we can valorize more material. So when we use this end-of-life wind turbine blade waste as a powder for cement replacement or for sand replacement or for fiber reinforcement, so we are limited to a certain amount of material that we can put on. So this was a very novel and lab-based application where we can create these little pellets which can replace the coarse aggregate in concrete, and then we can valorize more material and more waste into our new products. We saw from Tung the asphalt case, so how we can use the pyrolyzed and solvolized fibers as a reinforcement for asphalt application, for road applications. And of course, with Cynthia and Tao, we saw how we can primarily use the material produced out of these 3 pathways into reinforcing cement-based composites, and especially mortars, and how this compares to alternatives like steel fibers, basalt fibers, or glass fibers. So in all cases, we described the synthesis process. We had the primary application of these 4 novel products, and there was also a performance evaluation against a virgin case and also against our surrogate battle-tested solutions in all of these conditions. And the last part of our webinar was the industrial scale application, so how we utilize all this knowledge to pass it on to industry so that we can have immediate implementation of the research into real world and real scale applications. So Victor presented us a wide range of different trials that have been already implemented in the industry with great success. And also Rose showed us how is the in-depth life cycle analysis of this material. How does it mitigate, like modern challenges in terms of the environmental sustainability. So before we end this webinar, I think there is also a last round of a QR survey. So special thanks to Maria and Dionysis from NTUA who prepared this very nice and handy way of interaction between us and you. So again, we would like to thank you a lot for the participation and kindly ask you to scan one more the QR code you see on the screen and fill in the general Q&A survey before we thank you and before we just complete the session.